Okay, we're going to try a little review today for exam 6 on chapter 17. That would be spontaneous reactions, entropy, and free energy. I had a thought, man. Gone. Maybe it'll come back to me. I'm lucky. So this review is going to use both versions of the review documents, and I'm picking out, I think I counted 22 problems that I wanted to cover. Some of them are in version 1, some are in version 2. So let me scroll down to my first one in version 1, number 9. Oh, I remember now. Let's see that. And I put a bunch of formulas up here. This chapter is formula rich. It's got lots of formulas that we can use. So first one, number 9. At 1 atmosphere, liquid water is heated above 100 degrees. So we know that at 1 atmosphere, the boiling point of water is 100 degrees. But if we heat it above 100 degrees, then we're no longer at equilibrium. We've got a situation where where we use this one to answer the question, because delta S surroundings is what we're after. And that's equal to, now you can, if pressure is constant, then this can be delta H or it can be Q. But to be safe, I'm going to put Q in here instead of delta H. And the question is simply that, is this value 0, greater than 0, or less than 0? Or do we need more information? And if we're at 100 degrees, then the process is, let's see, so we've got our system, which is liquid water going to gas. Right? How does it get there? Well, it has to be endothermic. In other words, heat has to move in. Okay, so the value of Q in this case is going to be, for the system, is going to be positive, but for the surroundings, it's going to be negative. So Q for the surroundings is negative. The surroundings is losing heat to the system in order to accomplish this task. So that means this is going to be negative, and that makes the overall greater than 0. Right, we have a positive value. Now, why does it say less than 0? My reasoning is faulty. Let me see where I missed it. Oh. Q is always referencing the system. But, so if it's endothermic, then Q has to be positive. All right, that was my mistake. Q, if we don't put a subscript for Q, and we usually don't, Q is in reference to the system. So if Q is positive right here, then the overall has to be negative, and this is less than 0. Okay, that was my mistake. Did I confuse anybody? Okay. All right, number 10. Yeah, sort of. Get most of it, finish it off with a rag. Excuse me. At 1 atmosphere, liquid water is heated above 100 degrees. Now, what's the delta S for the universe? And these questions are created by the authors. And remember that their delta S universe is my delta S total. Okay. So we know that delta S total is equal to system plus surroundings. Right? We know this one is less than zero. Less than zero. And let's see, water is heated above 100 degrees. Right? If this were at equilibrium, then this value would be zero if equilibrium. But it's not at equilibrium. We've heated it above that point. We are adding heat. Okay? U is being added to the system. Surroundings is losing heat. Systems, we're adding heat, but we're exceeding. That energy entropy of the surroundings is decreasing. Energy entropy of the system is increasing. But since we're not at equilibrium, they're not equal. So if this one is going to be negative, then this one, of course, has to be positive, but it has to be a greater positive than this negative. And for this process to be spontaneous, this has to be greater than zero. Yeah, so if the process is spontaneous, then under these circumstances, delta S must be greater than zero. All right, let's see. Got that stuff in my way. It's not in your way, but it's in my way. Number 11. Which of the following statements is true? All right, we have A, B, C, D, and E. And we look at our statements, and we find that all of them, except for the last one, which says none of the above is true, all of them are referring to by spontaneous, we mean. Okay, so we're looking at what does it mean to be spontaneous? We want the best statement referencing what spontaneous means. Okay, spontaneous. A says spontaneous says we mean that the reaction or process will always proceed to the right as written, even if very slowly. Now that's true. That part of the statement is true. Second part of the statement is increasing the temperature may speed up the reaction, but it does not affect the spontaneity of the reaction. We know from our calculations that delta G can be positive under certain circumstances. We change the temperature and it becomes negative. So we know that A is false because of the second part of that statement. When you change the temperature, you can change the spontaneity of the reaction. Right, so A is out. That's false, based upon the second part of that statement. B says spontaneous, we mean the reaction or process will always proceed to the left as written, and that's false. Stop right there. As written, we mean spontaneous to the right. We mean it moves to the right without any assistance of any kind. C says spontaneous, we mean that the reaction process will always proceed to the left. Again, that's false. Spontaneous refers movement to the right. Okay, so D says we are proceeding to the right as written. Okay, that's good, even if fairly slowly. And then The second part of the statement, increasing the temperature may speed up the reaction and it generally affects the spontaneity. That is true. So E has to be false because we do have one that's true. Okay. Let's see which next one I picked. I'm going to skip a bunch. I think there's a lot of redundancy or repetitive types of questions in version 1 and 2. So I'm going to go down to 34. Give me good performance either. Let's try this one. In the following reaction, carbon dioxide and water yields methane and oxygen. Actually, that's the reverse of combustion. The delta H for this one is 803 kilojoules. That's a positive value. That means this process, we add heat to make it work. Which of the following will increase K? So with this reaction, I'm not going to put the reaction up there. I'm just going to use the delta H. The delta H is 803. Delta H0 equals 803 kilojoules. And since this is 0, this temperature equals 25 degrees C. Okay. We know that since this is positive, maybe I better write the reaction up here. Fa plus oxygen. And let's see, all of those are gases, so we don't need to write that in there. All right, what do we mean when we say this value here? We could use this equation and the plot because we have a relationship here that includes the delta H and the temperature and the K. But a simpler approach would be to use Le Chatelier. If this is endothermic, which side of the equation would that heat go on? This side over here. Yeah. So this is our delta H. Okay. Now what happens if we, which of the following will increase K? Well, how do we increase K? If K is equal to, let's see, this is 2 and this is 2, sorry. And this is O2 squared, and this is CO2. This is H2O squared. Then which one of these will increase K? Changing concentration doesn't change the K. K is constant, right? K is constant no matter what we do to these factors right here. The only way we can change K is temperature. If we change these values in here, K is always constant at a given temperature. So we need to find the one that references temperature. Increase the temperature of the system. Okay, if we increase the temperature, yes, we'll add this term. It will drive the equilibrium to this side. So when we're studying Le Chatelier's principle, changing concentrations, changing pressure, does not affect the K itself. It affects the equilibrium, but not the K. But the equilibrium is influenced by Le Chatelier's principle for temperature in terms of the value of K. That's the only one, the only disturbance that will change the K. And that's the explanation for a shift in equilibrium. When you change the temperature is the fact that the K changes. But for pressure and concentrations, the K does not change. All right. So C, increase the temperature of the system, will increase the K value. I could have saved us a whole lot of time and trouble just by doing that. All right. 36. Consider the gas phase reaction, NO plus half oxygen. Does, 2. And 2 and delta H0 is minus 56.91. Delta H0 equals minus 56.91 kilojoules. And K at 25 degrees is 1.46 times 10 to the 6th. And this is at 25 degrees C. All right, that's everything we're given. Yeah. What would be the effect on the amount of NO present, the amount of this present, by compressing the equilibrium system to a smaller volume while keeping the temperature constant? Okay, so we're not going to change the K value. We're only going to compress it. We're going to increase the pressure by reducing the volume. So in order to assess the effect of pressure change or volume change, we need to know gases. Are they all gases? Yeah, gas phase reaction. That means everything is a gas. To answer this question, we need to know how many moles of reactants and how many moles of product are in the stoichiometric ratio. So this one is 1.5 moles, and this is 1 mole. So if we increase the pressure on the equilibrium system, the response is going to be to try to produce fewer moles to relieve some of that pressure. So it would shift the equation to the right, and NO would be reduced. Okay, NO would decrease. Let's see. Do I have any more? Yeah, 46. All right, we're given the following data. Calculate the normal boiling point for formic acid. Formic acid is the simplest carboxylic acid. It's like carbon, and then you have this one. Very simplest carboxylic acid. And the boiling point for this would be changing this liquid to HBOH, that gas. Okay, and we're given the delta H is a formation and the entropies. All right, so what do we need to know to calculate the normal boiling point? Well, if all this happens at equilibrium, and we know that that means that let's talk about it this way. The delta S total at equilibrium is 0. And that's equal to delta S surroundings plus delta S system. So if we can find out what delta S for the surroundings is, and we have a formula for that, delta S surroundings is negative delta H over T. Negative delta H over T. That means this has to be positive delta H over T. And we're looking for this temperature. So we want delta H over T is equal to delta S for the system. So we need the delta S for the system, which is, and we go to our calculations for that. right? It's final minus initial. The final gas is 251 minus 130. 251, and this is joules. 251 joules minus 150. So I'm not going to rely on my brain. That I should be able to do that. Yeah. My pattern this morning is making too many mistakes. So this is that's not, yeah, that's right. 101 joules per K. Because this is 1 mole each. So we already multiplied that by 1 mole and got rid of the mole term. So that's delta S for the system. Excuse me. Delta S for the system. Now we need to know delta H. Delta H is equal to what? Final minus initial. So gas minus liquid. 251. Oh, hold on a second. I'm in the wrong column. Minus 363 minus a minus 410. Okay. And that will be 410 minus 363 is 47. This is plus, these are both plus 47. And these values are kilojoules per mole. So this is simply kilojoules. All right. Yes. So we get 20 of them back, right? Okay. Okay. So the calculation here, delta S system equals delta H over T. We solve for T, right? Then it's delta H over delta S system. But we've got a unit problem. Our units have to match. This is kilojoules. This is joules. So we got to do one of two things. Convert joules to kilojoules or kilojoules to joules, and it's easier to do this one. So this temperature would be, delta H would be 47 times 10 to the third joules per, no, just kilojoules, just kilojoules. And then delta S system, we can leave it as is, 121 joules per K. So joules will cancel, K will flip into the numerator, and we'll have our value in terms of K. So 47 exponent 3 divided by 121 is, this should be 388. Calculator only spits out what you put in, and I put in the wrong stuff. So this is 273, and that's 115. Yeah, that that last value wasn't even reasonable. You know anything about formic acid? You go up to that high temperature, and you're just probably going to combust it rather than vaporize it. So the answer is E, 115. Oops, skipped. Here we go. 52. Okay. We want to calculate the delta G for water plus oxygen yields hydrogen peroxide at 600 K using the following data. Okay. And this is standard temperature and pressure, 25 degrees in 1 atmosphere. Calculate delta G0. So the equation we've got is water plus half oxygen. Water plus half oxygen is an equilibrium with hydrogen peroxide, right? Yeah. And at 600 temperature, 600.1 K. All right, that's not standard. This is, we get the following data at 600. So this is current temperature equals 600.1 K. Question is, we want delta G at standard temperature. All right. And what are we given? Oh, we're given two equations where we can calculate the K. And once we get the K, then we can use minus RT log. This one right here. We need the K value. Okay. So we're going to have to use Hess. Let me move this out of the way. This is our target equation. And we have, let's see, the first one gives us hydrogen peroxide. So if we use the first one, H2 plus O2 is H2O gas. And that has the correct number of moles, right? So that gives us this one. And this K value is 2.3 times 10 to the sixth. Okay, 2.3 times 10 to the sixth. And that's KP. This is KP. All right. This has a whole oxygen. We only get a half an oxygen. So the second one puts the water on that side. We need to move it to this side. So we have to flip the equation. H2O. H2O is in equilibrium with two hydrogens and one oxygen. Let's see if I did that okay so far. We're going to put the bases in here. That one, that one, that one. This covered that value. And if we put this one in, this is two there, and this is 2 here. If we invert this equation, we invert the K, right? Y'all knew that already. I just didn't follow through. All right, so it's for this one is 1.8 times 10 to the 37th is the inverse of. Okay. There. So that's 5.56. This is equal to 5.56 times 10 to the minus 38. Then we take the square root of that value. And that gives us this one. 2.36 times 10 to the minus 19. Okay. Now we're going to use this one times this one. Those two. So I already got that one in there. I'm going to put the other one in. Exponent 6 times. So the overall KP equals 5.4, and I'm hanging on to a decimal point, times 10 to the minus 13. That's the KP. Let's see if I'm on track. Yeah. Okay, next. Oops. Next, we can use our formula. This one. So if the question was, what is the delta G under standard conditions, delta G 0, we have minus R, which is 8.3145 joules per mole K, times T, which is already in K value, 6.101. Go. And then the natural log of 5.42. That should give us our delta G under standard conditions. 8.31. Just go ahead and change that sign. 600.1 and then 5.42 exponent. Change the sign, do the natural log of that one first, and then multiply. Okay, so now I'll get 1.409 times 10 to the fifth. This in kg? Yeah, kilojoules. This is in joules. So kilojoules would simply lose 3 of these. So kilojoules would be 1.409 times 10 to the second kilojoules, or move it over 2 places in case it's, say, rounded off, 141 kilojoules. Okay. Did I lose you? All right. It's the R value. Yeah, yeah. And I'm sure it's in useful information. It's the one when we were doing gas laws and we had R's, we were using 0.0 something. But this has energy involved, so we have to use a different R, 8.3145. All right. Then we're going to 53 next. Unless there are questions. Any other questions? Okay. I'll tell you, the details will sink a ship every time. $53. Let's scroll up a little bit. 53 is based upon this equation. 2NO2 equilibrium gas. 1 N2O4 gas. And the delta H under standard conditions is equal to minus 56.8 kilojoules. And the delta S is minus 175. Delta S minus 175 joules per K. Okay, what else are we given? At 298 K, which is 25 degrees C. So temperature equals 298 K. N2O4 and NO2 are mixed with initial partial pressures of 2.4 and 0.42, respectively. So N2O4 comes first. That means N2O4 is 2.4 atmospheres. And 0.42 this. Okay. Which of the following statements is correct? Some N2O4 will decompose into NO2, or some NO2 will dimerize to N2O4. System is at equilibrium. Final total pressure must be known to answer this question. Okay. So what do we need to know to answer, say, the A or B, or in fact C, if we know it's at equilibrium? Some N2O4 will decompose, or some NO2 will dimerize. we need to be able to determine, let's see. Yeah, compare the K with the Q. We can calculate the Q, simple. We got all the information we need to calculate the Q. And we can do that right now. That's equal to this one, pressure of 2.4 atmospheres to the first pound, and then NO2 is 0.42 to the second pound. Okay. It's the K that's going to take some time and effort. And then 0.42, square that one and divide it into. So this value is 13.6. 13.6. So we need to know the K so we can tell which way the reaction is going to move. All right, the way to get the K, we have access to delta H, delta S, which means we can calculate the delta G. And we also know that delta G is equal to this equation where we can find the K. So in the worked problems, I combine those two equations so I'd only have to do one calculation. But we can do both of them separately. We can just say delta G equals delta H plus delta G 0 equals delta H 0 minus T delta S 0. We can calculate the delta G. All we need is the correct units. And I always go for converting to joules, so it doesn't give me a small fraction. So this delta H would be minus 56.8 times 10 to the third joules. And this temperature is, let's see, are we given a different temperature or is this all standard? It's all standard, 298. So this would be 298 K times delta S minus 175 joules per K. Like that. So that'll give us delta G 0. Let's see, I'm going to do this one first. 175 and 298. And a negative times a negative makes that positive anyway. So I can leave it like it is. This gives me 5.22 times 10 to the fourth. Joules, because the K's cancel. And then this is added to, since both are negative, this is added to 56.8, change the sign, exponent 3. Add those together. And we get negative 4.65 times 10 to the third joule. Okay. So now that we know that value, we can use this formula. Delta G0 equals minus RT log K. All right. So let's solve for log K first. Then we have delta G0 divided by negative RT. Delta G is minus 4.65 times 10 to the third joules. And negative R is 8.3145. And T is 298. Okay. So I've already got this one in my calculator. I just need to divide by 8.3145. Dyslexia gets change the sign. And then divide by 298. And I get 1.88. as log K. That's log K. So how do we get K? Remember what logs mean. That value is the power of E that equals this value. So we say E to that power. I got that value in here. I'm just going to hit the E to the power button. 6.5. Okay, now we have K and we have Q. Q is greater than K. Q greater than K, which means what? If Q is greater than K, we got too much product. Right? This term is too high to make Q, or this term is too small, both of them. So that means it has to shift back this way and reduce that one and increase this one to reach the K value here. So that means it has to go back this way. N2O4 will decompose. Okay, that's a lot of work just to answer a simple question. I'll grant you that. Did I lose anybody?
How do you solve on the calculator?
Oh, on your calculator, you look for the E to the X power. But I mean, that's the way mine is listed. And it's usually what do they call it? Press the function key.
Second.
Yeah, second. And it's usually listed above the natural log key. So you'll have on the key will be ln and above the key will be e to x.
You just press that and it's 1.8.
Should be, yeah. Get most of it. Add eraser, rest of it with a rag. Cleans up. Usually go 2 or 3 problems without this, but then the video picks up the shadows from previous problems. Okay, let's see how many more. We got 56. 56. Six. So this system is at 25 degrees, standard temperature, and we're going PCl3 plus CO2. PCl3 plus Cl2 is in equilibrium with PCl5. And the delta H under standard conditions is minus 92.5 kilojoules. Yeah, delta H 0 equals minus 95.2 kilojoules. Okay. If the temperature of the system is raised, the ratio of the partial pressure of PCl5 to partial pressure of PCl3 will apply. This one ought to be pretty simple, right? If we just use Le Chatelier. Yeah. Okay. This is a negative number, right? Which means it's exothermic. And that puts the heat term on this side, right? Okay. If we raise the temperature, is that what it says? Temperature is raised. The ratio of the partial pressures of PCl5 to PCl3. So what we want is PCl5, actually, the pressure of PCl5 to the pressure of PCl3, partial pressures, is going to do what? Right? If we raise the temperature, we're causing PCl5 to decrease. Right? So the ratio should decrease. We're going to decrease this one and increase that one. So the ratio should decrease. Okay, I didn't pick 57. Oh, let's go ahead and do 57. Same problem, different scenario. What's going to happen to the ratio if we decrease at constant temperature? Volume is decreased. So we're gonna change the volume by decreasing it, increase the pressure. All right, so we have 1 mole gas on this side, and we have 2 moles on this side. So if we stress the system by increasing pressure, decrease the volume, it's going to try to make fewer moles. Now we're going to shift to the right, and that will increase. Ratio will increase. Okay. Let's see. I did mark 58. Oh, and we've got another problem in version 2. Number 56 is related to 58. So we're going to skip to that one. As soon as we finish 58 in version 1, we're going to go to version 2, 56, because the same conditions hold. I don't have to write it up here again when I get to it later. So we're still in version 1. So we're gonna do 58 first. The equilibrium constant in atmosphere is for the dissociation reaction of Cl2 to 2Cl was measured as a function of temperature in K. Okay, so we're going from Cl2 to 2Cl. Cl2 and the equilibrium 2L. And we've broken, in other words, to go from here to here, you break the bond. Go to here, you form the bond. Okay. Other conditions. Let's see. A graph of natural log Kp versus 1 over T. That looks like this one right here. What does that graph look like? Gives a straight line with a slope up. Okay, so let's put the graph up here. Okay. We've got 1 over T. Okay. So that would be the K to the minus 1, be the units for that one. And then log K. 2 different K's here. Would give us a straight line with a slope, a negative slope. So it's going in this direction. And slope is equal to minus 1.651. 0.651 times 10 to the 4th. And an intercept of 14.51. So it's going to intercept the y-axis at 14.51. All right, we know that slope is equal to minus delta H over R. Minus delta H 0 over R. And the intercept is equal to delta S 0 over R. We may or may not need it. I'm just putting that up there so I won't have to think about it afterwards. All right, from these data, which of the following statements is true? The reaction is exothermic, the reaction is endothermic, the reaction rate is high, the reaction is non-spontaneous. All right. And none of these. So if we find one of them, then E is wrong. We just have to find the one that's right. Okay. If we want to know something about exothermic or endothermic, we're looking at delta H. Okay. So we're focused on this term right here. If this is negative and that's negative, then delta H has to be positive, right? Yeah, delta H must be positive. That means it's endothermic. And B should be the answer then. Can we say anything about the reaction rate? Not from this information. We're talking about equilibrium, right? The reaction rate is kinetics. How about the reaction is not spontaneous? Well, we would have to solve for delta G to find that out. And if we say, all right, if the slope is this value, right, times 1 over t, let's go ahead and do that calculation just out of curiosity. Delta G 0 equals, and we have a minus 8.3145 for R, and then, excuse me, use your brain, Dave. This term right here, which is 1.6541 times 10 to the 4th, and that is times 1 over t. So 1 over 298k, because we're at standard. And then plus this term right here, 14.51. So 1.6541, change the sign, exponent to the 4th, and 298 divided into that, and then 14.51 plus. So that gives us a minus 41. Units. Joules. Right. But it's a negative number, which means it is spontaneous. So D says the reaction is not spontaneous, and this calculation says it is spontaneous under standard conditions. Okay. All right, we're going to skip down to number 56 in version 2, and I've got both of my documents spliced together, so all I have to do is scroll down. Go down to 56. Close, close. Keep going. 56. Here we go. All right, we got the same equation, same conditions. The value of delta H for this dissociation reaction is what? So we're going to remove this here and change this to 56 version 2. Okay. All right. We know that this value is equal to that value. So all we need is what is R. We say minus 1.6541 times 10 to the 4th equals minus delta H 0 over 8.3145. Okay. So if I bring this one over here and multiply it by that, why not bring that negative with me? I'll just take negative over here at the same time as this one, and that will change this to a positive. So 1.6541, correct? No, 651. 1.6. Where did I get 41? There. 1.651 exponent 4, and then times 8.3145. And we already changed the sign. So delta H equals 1.37 times 10 to the 5th joules. Oh, we're in kilojoules. All right. This should be positive. Yeah, positive. That agrees with our previous assessment, our semi-quantitative assessment. This is the quantitative assessment. It needs to be in kilojoules, right? Okay. So just reduce this one to 10 squared, right? Take 3 of those out. And that's 1.37 times 10 squared kilojoules, which in standard notation is 137 kilojoules. There you go. Positive 137. B would be your answer. Okay. Now we can go back. Let's go back to 58 in the first one and see if there's anything left in the first. There's 58. We skipped. Now 59 in version 1. We're back in version 1, number 59. For a certain process at 300 K, temperature equals 300 K, delta G is minus 10.4 kilojoules. Minus 10.4 kilojoules. And that's at this temperature. This is not standard conditions. That's at the temperature given. Delta H is minus 7. Delta H equals minus 7.0 kilojoules. Okay. If the process is carried out reversibly, the amount of useful work that can be performed is. This is simpler than it looks. Delta G is the maximum amount of work that then can be extracted from this process. Right? And the sign is going to be the same. So W max actually equals delta G. So that's equal to minus 10.4. Kind of a trick question. All right. Okay, now we're in version 2. Again. Let's change this. I think from now on is version 2, except for when we get to 56, we'll just skip it. Okay. A 2-bulb flask contains 5 particles. What's the probability of finding all 5 particles on the left side? We got a flask here. And then we got one here. We have 5 particles, A, B, C, D, and E. What's the probability of finding all those particles on one side? Well, what's the probability of finding 1 particle on one side? 1/2, isn't it? That's probability of finding 1. Finding 2 is another half. Finding 3 is another half. Finding 4 is another half. Finding 5 is another half. So that's 2, 4, 6, 8. No, 2, 4, 8, 16, 32. 1/32 is the probability, but we've got it in percent, so we need to find out what that fraction means. So, and times 100, since it's in percent. 3.125. 3.125% probability. Or 3.13 rounded off. Okay. The other way to do that, since we have 2 flasks, right? If we had 3 flasks, it would complicate things. But with 2 flasks, we just say, all right, with 2 flasks, it's 2 to the 5th power. 1/2 to the 5th power. If we had 4, it'd be 1/2 to the 4th power, or 6 to the 6th power. Finding all of them on one side. Okay. Then scroll. Oop, there's one. 14. Trichloromethane. Okay. CHCl3 solid. CHCl3 solid is in equilibrium with liquid. CHCl3. This has to occur at a low temperature. What is the melting point? Okay. So the melting point for 14. Now, when it says when the question is melting point, we're talking about equilibrium. So we can use the relationship where delta S total at equilibrium is equal to 0. And that's equal to the sum of delta S system plus delta S surroundings. We know this one is equal to negative delta H over T. So this one has to be equal to delta H positive over T. They have to cancel each other out to give you 0 here. So this is the one we're going for because we're looking for that temperature for the system. All right, what values do we have? We have delta H and delta S. Okay. And these are under standard conditions. So delta, let's see, T then would be, bring it over here and bring this down, would be delta H over delta S. So remember, if we don't write anything under the S, it's automatically system. But they have to be the same units. So I'm going to change the delta H from kilojoules to joules, 9.18, 9.19 times 10 to the third joule. And delta S then would be just as is, 43.9 joules per K. And this is all 1 mole, right? 1 to 1. So I don't have to include the moles. Joules cancel, gives us K. Let's see, 9.19 exponent 3 divided by 43.9. And this is 209 K. Temperature is in degrees C. So minus 273. I was right. It's going to be negative Celsius. 273. So that's 64 minus 64 degrees C. Okay. That's the melting point of trichloromethane. If you pull a bottle off a shelf with trichloromethane, it's going to be in this phase right here. Good. I guess unless you live at the North Pole or the South Pole. Okay, number 20. In which case must a reaction be spontaneous at all temperatures? Okay, let's go back to Gibbs free energy. G equals delta H minus T delta S. Okay, and we want a negative delta G under any case of temperature, all temperatures. This has to be negative. Okay, so how do we get there? Well, the best way to get there is for both of these terms to be negative. Right? So this would have to be negative. This would have to be positive. So which one fits that? Delta H is D. Delta H is negative. Delta S is positive. Yes, that'll give it to you at any temperature. Under what circumstances would this be positive? Non-spontaneous. Well, this would be negative, and this would be positive. Okay. In case I get sneaky and change the question. All right. That was 20. I'm doing on time. Okay, we got an hour before this is due to terminate. 26. When a stable diatomic molecule spontaneously forms from its atoms, what are the signs of delta H, delta S, and delta G? Delta H, and G. And the process is a diatomic molecule forms from its atoms. So we have to have two of those atoms under gaseous conditions spontaneously forms a diatomic, like that. Okay, that's what that means. All right, spontaneously forms. That means this has to be negative. That guarantees spontaneity. And then if that's negative, then delta G equals delta H minus T delta S. Where's this? Okay. Let me see if I can solve it this way. If I can't, I'll do it an alternate way. If this is going to be negative, excuse me, this is negative, sorry. If this were at a lower temperature, like standard conditions, then this could be negative, right? And still give you a negative value. All right, let's look at what delta S could be. Delta S refers to the system entropy. We're going from more disordered to less disordered. That makes delta S negative. So that answers this question. This has to be negative to go spontaneously that direction. This is negative, but the conditions tell us that the measure of disorder decreases. So all of them are negative. All right, we can also reason delta H. If you've got two separate atoms and they come together, they're going to give up energy. Right? As the bond forms, more stable is lower energy. That energy's got to go somewhere. So that's over here. That makes this negative. So that's negative. This is negative. And this term could be positive, but it's better negative because we've got a decrease in disorder. So that makes this negative. Okay, that's a better line of reasoning. Okay, let's see, down to 31. All right. Okay. So we're given calculate the KSP, solubility product, for sodium chloride. So the solubility product is going to be the solid is going into solution to produce sodium ions and chloride. Okay. And the KSP, we may not need this, but here it is. Okay. The information we're given is in terms of delta G. the delta G formation for each of these. So if we can find out the overall delta G for this reaction, we should be able to calculate the K under standard conditions. Okay, so what's the delta G for this reaction is products minus reactants. And since there's 1 mole of each, we just use the values as is. So sodium chloride, sodium and chloride, minus 262, minus 131, okay, then subtract sodium chloride, which is minus 383.8. Okay. And this is in kilojoules. Okay. Calculator. 262. One, that's minus 393. And then plus negative times negative. 383.38. That's minus 9.2 kilojoule is delta G. See if I'm still on the right track. Yep. But these values have to be in the standard units, which means we need minus 9.2 times 10 to the third joule. Now we can use this equation and find out what KSP is. So we have delta G0 equals minus RT natural log K, in this case KSP. And let's solve natural log KSP equals delta G0 over negative RT. So we know what delta G is minus 9.2 times 10 to the third joules. And then R is 8.3145. And T is standard condition, 298. There we go. Negatives cancel negatives. So let's see. That's in the numerator, 8.3145. That's positive, excuse me, 3.713. 3.73. And here we go. KSP is equal to E to the 3.713. Change that sign and do E to the X is 41. 41 is close as I can get. Okay. That's your solubility product, which means sodium chloride is very soluble. It's spontaneous at room temperature. Okay, 34.
Yeah, it's not with 36 on the last one.
Let's see. So we got NO plus half oxygen. NO. One. Equilibrium with NO2. Delta H is minus 56.91. 56.91. kilojoule. And K is 1.46 times 10 to the sixth. Okay, at 25. Okay. Now the question is, for this system, if it's at equilibrium, we raise the temperature, how will it affect the concentration of NO? Oh, this is simple. This is an exothermic reaction. That puts delta H on this side. We raise the temperature, we're going to drive the reaction back this way and increase the NO. Now, the amount of NO will increase. That's A. Okay. And let's see, who's next? 40. It's just definition. Second law of thermodynamics states what? The second law of thermodynamics approaches the concept of entropy, or the S value. And during a spontaneous reaction, let's put the first law of thermodynamics is delta E for the universe equals 0. Never changes. That's conservation of energy. Second one says that the entropy for the universe, and I do mean the universe, the whole universe, is always greater than 0. So, well, actually, we can restrict that. The delta S total for a spontaneous process is always greater than 0 also. Right, we want to be specific. So a B would be a good answer for that one. I'm not going to bother with the third law. Actually, there's a 0th law. You know that? They decided after they had the first, second, and third laws in place, they said, uh-oh, we're missing one. So they put in a 0th law. Huh? No, because the 0th is more pivotal, instrumental for the others. It needs to come first. All right, 42. Mixture of hydrogen and chlorine remains unreacted until it's exposed to ultraviolet light from a burning magnesium strip. Then the following reaction occurs very rapidly. Okay, we've got this glass bulb or quartz bulb. So light can pass through, but we can put energy into it, but we can't put matter into it. So let's see, that's not, see, isolated is both open, closed. It's a closed system. This is closed. That is no mass transfer. No mass transfer. But energy transfer is allowed. Right. So this is a glass sphere. And inside we have hydrogen and chlorine gas. Okay. They're just sitting there. They're not doing anything. So they're not making hydrogen chloride gas. At least not very rapidly. But if we have this burning magnesium strip, then we allow, right, H nu, remember that's equal to energy. And this is coming from Magnesium plus oxygen yields magnesium oxide. And this would be, let's make that 2 and this 2. And that gives you the light. So the energy can go in here, and what that is saying is this energy is supplying activation energy for that reaction. Okay, so if the delta G for this reaction is negative, then it is spontaneous. Delta G is negative. Delta H is negative. Right? Delta H is negative, so it's exothermic. I drew this correctly. Exothermic. And delta S is also negative. So what we're saying is we're going from 3 moles here to 2 moles. We're going from a solid and a gas to a solid. So we're losing the positional entropy of the gas, and we're making it all solid. So you can look at it 2 ways. 3 moles to 2, or solid gas to solid, means entropy is decreasing. It's negative. Okay. All right, what is the following? Which of the following is consistent with this information? Well, the reactants are thermodynamically more stable than the products. No, thermodynamics has this versus this, and forget that. And if it's exothermic, that means the products are more stable than the reactants. So A is false. Let me put those up here. A, B, C, D, E. This one's false. B, the reaction has a small equilibrium constant. It can't have a small equilibrium constant. If the value of G is negative, it's spontaneous, and the products have to be favored, which means the equilibrium constant is greater than 1. Okay, so B can't be true. C, the ultraviolet light raises the temperature of the system and makes the reaction more favorable. All right, we're told, let's see, are we told? We're not told anything about the temperature. I don't see any comments about temperature. Ultraviolet light could raise the temperature of the system, but it wouldn't make the reaction more favorable because we already know it's favorable. It's not going to make it more favorable. If it raised the temperature, what would actually happen? 42. All right, these photons carry enough energy for the activation, but they don't carry enough energy to affect the temperature. So C is also false. I didn't go into a lot of detail on that one. The negative value of delta S slows down the reaction. Does it? Oh, simple. Right? All these terms are thermodynamic terms. They say nothing about kinetics. Right? The kinetics is supplied. So the negative value of delta S doesn't say anything about kinetics, which makes it also false. And then E, the reaction is spontaneous, yes, but the reactants are kinetically stable, yes, because they don't do anything until we add some energy to them. Until we make it over this hump, they're happy to just sit there and do nothing. So they're kinetically stable, but they're thermodynamically unstable, which tells me that if we wait long enough, we'll end up with products. It just may take several centuries. All right. Who's next? Skipped a few. Okay. Probably have to look it up just to be sure. Should have given false information. 52. The equilibrium constant of a certain reaction was measured at various temperatures and give us this plot. What is delta S for the reaction in joules per mole? K. Delta S. We're looking for delta S. And we've got this equation. So we know that the y-intercept is going to give us information for the delta S. So delta S over R is equal to what? Where does it intercept? The natural log of K is equals. No, it's that value itself is 3. Yeah. Okay, so now delta S is equal to 3 times 8.3145, which is that term right there. So it's about 24, 25, 26, 25. 25 is close enough. Approximately 25. So we can do that without a calculator, with a multiple choice test. That's going to bug you until I find out what the name is. I'll find it eventually. All right, 50. Oh, we did 56 already, didn't we? 57. For a certain process at 300 K, temperature equals 300 K. Delta G is minus 12.2. Delta G minus 12.2 kilojoules. And delta H is minus 7. H. 7 kilojoules. If the process is carried out so that no useful work is performed, delta G, well, delta G is what it is. If you don't get any work out of it, that doesn't make it 0. It's still a value, right? So delta G is still negative 12.2. That's a trick question. You didn't get any work out of it. That just means all of that useful energy, that free energy, was wasted. That was easy. Oh, we're done.